project I was working on, which is improvements to PyPy's implementation of NumPy, which is a Python library for doing numerical and array computing. So now I'm going to talk about sort of the result, or at least so far the results of the work. So I think the first step is to understand sort of NumPy is built out of a couple very closely interlocking building blocks, which is sort of the basis for all the operations. And sort of the most fundamental level is it has an array class, which is a multi-dimensional array, and basically you can do a bunch of operations on it. You can build arrays of varying types, and they basically all operations, all of them work sort of element-wise, and they're sort of the core building block for everything NumPy has to offer. The next building block is dtypes, which is our way of specifying the data type for any given operation. And basically you can coerce anything in the NumPy world into a data type. So the Python built-in float type corresponds to a 64-bit double. The character I2 is a 2-byte integer int16. Q is the type code for a 64-bit unsigned integer. So you have all these sort of different built-in data types. And NumPy has a bunch of boxes for objects. Your dynamic language like Python, everything is sort of an object. But Python's built-in integer type is whatever the system long size is. A float by default is double, so it's 8 bytes. And basically NumPy provides tons of different boxes for each of the other types. So you can see if you get that 0 back out of the array, it comes back as NumPy's 64-bit int type, since I'm on a 64-bit platform. If you create an unsigned integer 260, it's supposed to be uint8, it's supposed to be an 8-byte int, so caps at 256, so it rolls over to 4. So we have all these different types that need to be implemented. And there are ufuncs, or universal functions, which are these suite of functions that NumPy has that are sort of the core of these working over all different data types. So you can see it works over sign, works over a scalar 3, it works over a Python list of 3 numbers, and it also works over an array of booleans, which sort of it has all this logic for how different types get coerced. And so taking the sign of an array of booleans actually returns an array of 16-bit floats rather than a full 64-bit with floats. So you can see there is a slight precision difference between the sign of 1 as an integer and the sign of true, because there are different size floats in the result. And so at the start of the semester, we had mostly working single-dimensional arrays with many of their methods. You could read values, you could write values for various data types. Yeah, so we had many working universal functions. So we had all the basic ones: add, divide, sine, the trigonometric ones, the basic arithmetic ones. But they didn't support all their methods, so you can only do sort of the very basic calling interface with them. We had some of the built-in data types, so the really common platform with integers, but not all the unsigned integers. We only had 64-bit floats, stuff like that. And we had no boxes, so for every operation would upcast its result to whatever the platform size is. So everything returned a 64-bit float, and sort of you get stuck with whatever the rounding error was. However, to understand sort of every part of how the entire NumPy system fits together, I think the most important thing to understand is it's all about the data types. Sort of the data types control all the operations that go on. They understand the shape of the arrays, their memory layout, things like that. So a big part of the work I did this summer was sort of this semester has been refactoring the entire data type interface. And unfortunately, data types are not simple things. They are in fact a giant mess. Because data types are not just these nice flat primitive structures. You can also create your own custom data types that say have an x and a y float fields. So we have a point data type. And then we can create another data type that uses that. So we can start nesting these things. We have complex data types, so it's both a real and an integer part. And this is where kind of the rails start to come off the track. The train comes off the rail. And so this semester there were a number of horrific failures in pursuit of implementing these complex values. So the first attempt was implementing complexes as an array of structs. So we created the struct object, and we created a new d type, and we said the type for this is this double complex structure. Unfortunately, even though at certain levels this struct is sort of substitutable with a primitive type like a long or a float, there are a lot of ways it's not. For example, passing around an instance of one of these structs means passing around multiple memory locations, which has various crazy semantics across calls, and if you're implementing your own compiler, that sort of thing turns into a mess really quickly. And also, the rules of RPython, the language PyPy is written in, don't allow you to set an entire struct at once inside of an array. You have to set each individual field. So sort of having this work automatically and nicely by just saying, hey, the type of this is a struct, was sort of a no-go. The next approach was to sort of just say, okay, we can't do it automatically, we'll make them special. And the level of mess this entailed is far too gruesome to document. But of the many tries I had to make them special, there was the version that required rewriting almost all the code, there was the version that leaked memory like a sieve, and I forget what the last version was, but it was worse than both of those combined. No images available of this disaster. And after these several failures, I reached sort of a software engineering nirvana, when I realized that 0 is less than 1 is less than n is less than 2. Writing something 0 times would be optimal. Writing something once is, of course, okay. If you want code that actually does something, you have to write it at least once. But the second you say, I want to consider the case of 2, you need to stop and just consider the case of n. Because my mistake was I was thinking about complexes as, okay, these are these structs that have 2 fields, rather than, okay, I want to be able to represent arbitrary bytes and arbitrary sizes and arbitrary shapes, which I should have known better to because I knew there were the custom d-types from the beginning. So I invented the separation of d-type and item type, where d-types are these structures that are exposed in Python. NumPy has certain APIs to expose, so we have to keep implementing them. So d-types are something that are exposed in Python. But item types are this internal structure that knows about different types. And so there's a very nice separation of responsibilities to them. Internally, d-types are responsible for malloking the memory of an array, but an item type is responsible for knowing how many bytes it takes up. So the d-type can know how many bytes it needs to allocate. A d-type has all sorts of Python level properties, like it has a name and it has a specific number. NumPy numbered all their d-types for some reason. I don't really know what the motivation is there. And an item type has sort of fundamental low-level operations, like it knows how to coerce different values between each other, how to put values in these boxes, and how to perform all the really low-level operations. So we have an add implementation, and we have an add for 16-bit floats and 32-bit floats and all these other widths. Of course, we did clever metaprogramming, so we only wrote add once, but we have implementations for all these different bit widths. So the question is, how does this solve any problems in terms of these custom d-types? And the answer is we can have a composite item type, which is essentially just built by putting together multiple other ones. Basically change the thinking from the 2 or the n case is special to thinking primitives are special. Most things are they're composite types of some sort. Complexes are composites with the slightly special case that you know how to add them, you know how to divide them, you know how to perform all these arithmetic operations. But all composites are sort of the same in that we have this memory layout that's just a bunch of bytes. And so that was sort of the key breakthrough. And composite types work really nicely because you're able to just delegate all the operations. So for example, implementing the read an item out of an array for a composite data type is really simple. We simply iterate through all the types and we read the memory out of those and we build this composite result. And we do this because we're able to just keep track of the memory, so we track where our offset into the memory for each item in an array is. And similarly, storing is the same. You take your composite box and you simply unpack it one type at a time and write it into memory. In the progress of this incredible simplicity, we reached a three-headed yak in need of shaving. Anybody get the Monkey Island reference? Okay. So, quote from Antonio Cuny, who's one of the other PyPy developers. PyPy is a race between people shaving yaks and the universe producing more bearded yaks. So far, the universe is winning. Are people familiar with the phrase yak shaving? Alright, for those who aren't, yak shaving is essentially the process of, I have a task I want to complete. Here are all these other seemingly irrelevant tasks that I must complete in order to finish the task I actually care about. So the first one is I had to teach the JIT about the just-in-time compiler about reading items out of an array at a fixed offset. So essentially, you have to learn how to translate this very generic compute an array, compute in memory where an item in an array is at a specific offset is, and turn that into a single operation that it could understand. So right now it seems like a series. Before my work, it saw like a series of arithmetic operations on pointers and whatever that works. But it would have been significantly less efficient. Before it sort of saw read item out of an array, but now it's seeing all these different memory operations and has to learn sort of what their semantic meaning is. Once I taught it that, it was of course necessary to optimize the x86 backend so that for simple cases it's as fast as the old way. x86 has all this fun addressing operations you can perform in different operations, and so the more basically the more stuff you can stuff into your move operation instead of having them be raw arithmetic, the better. So I can teach it that if the width of a struct is a specific, if it's 1, 2, 4, or 8, you're allowed to use this special operation form rather than the slower, more generic way, which works because if you have the simple case where your item type is just a primitive, its width will be just 1, 2, 4, or 8. Another fun one, for NumPy's types, they have some nice multiple inheritance. They have both their own hierarchy of types. So you have generic, number, integer, signed integer, 64-bit signed integer. But if you're on a 64-bit platform, 64-bit signed integer also inherits from the built-in int type, just for fun. And so before it was not possible in RPython to write this multiple inheritance of built-in types. It was possible at the Python level, but it needed to be implemented at the RPython level, so where all these types are, because they have different memory widths that aren't naturally exposed in Python. So I've exterminated all the yaks. I'm sort of praying they don't breed further. So sort of there's some other things that also worked on, but were less sort of exciting from an architectural point of view. Multi-dimensional arrays. Like I said at the beginning of the summer, we just had, or beginning of the semester, geez. We just had single-dimensional arrays and Fortran to PyPy, which is awesome. So people wrote lots of really optimized numerical algorithms in Fortran. We don't really feel like reinventing them. So someone who's not me was working on Python has a library called C-types, which is a way to basically call out from Python directly into C without needing to write any C code of your own. And he basically wrote this code that lets you call into Fortran using the same mechanism. And so once we expose sort of the raw memory at the Python level, you'll be able to combine this with that and call into Fortran and use their advanced, like, I don't know what algorithms they use. I don't actually know any of the science stuff behind it. I just think it's a cool software project. Another fun part is we have awesome tests. So for reasons I'm not really clear on, someone decided the best way to write this. We like writing unit tests for our code, so we wanted to be able to test that these operations were as efficient as we wanted without needing to load up the entirety of the Python sort of ecosystem around it. So we have this mini numerical computing language where 30 with the bars around it creates an array that's 0 through 30. You know, the arithmetic does sort of the pairwise arithmetic. Sum computes the sum of all the items. And so we're able to really efficiently check exactly what operations the JIT would perform without needing to actually test the machine code generation or have all the Python stuff in the way. So sort of we establish in other unit tests that we can eliminate the Python overhead, and we eliminate this once that the numerical stuff is actually efficient. So sort of as a result, our status is now we have n-dimensional arrays on a branch that are almost ready, less a yak or two, yay yaks. We have most ufuncs with cool advanced features, like they have a reduce method. So you have an add ufunc, which does a pairwise add if you pass it two things. But if you pass it one array, you can call the reduce method with one array, and that's the equivalent of implementing sum. So now the sum method on an array can actually just call in this reduce method. We have almost all the built-in D types. The only notable exception is float 16 because C compilers don't actually support 16-bit floats. So the NumPy implementation is a scary thing where they cast it to an integer and like reinterpret the bits, and it's a scary disaster. And my interest in like dealing with 16-bit floats that no one uses anyway is like really, really small, like non-existent. And we also have the custom and the complex D types on this branch almost ready to be merged. And now we have also on the same branch we have this full support for all these boxes, so stuff always stays at the appropriate bit width. So thanks to the ArcOS program, Professor Morky, and everybody else. Questions?
So IEEE defines two different conflicting standards for 16-bit floats. Did you just pick one, or did you implement both?
No, I don't know how the original NumPy does it. I just punted on 16-bit floats for now. The stuff, if you have a result that would return a 16-bit float, it just gets upcast to 32. Because, yeah,
Okay.
multiple conflicting standards apparently. C compilers don't have like native implementations usually. Zero interest.
GCC at least, GCC and LLVM both support them with extra flags.
Like intrinsic operations or something.
No, it's just if you add a compile flag, it'll implement like something or other 16. You can do that, but I don't think Visual Studio does.
Okay. More fun.
Have you done some timing framework? How does this compare with the regular Python?
It compares pretty favorably. If you're sort of writing Python level algorithms, sort of reading individual numbers out of arrays and stuff like that, it's like much faster, on the order of 50 times faster. And if you're doing sort of using the native built-in pairwise operations, we're on the order of like 30% faster. We're looking to get even farther by using SSE2 and stuff like that. Packed operations. Any other questions? Cool. Well, thank you guys.